pleased to have Professor Rafael Sorkin start the session. Thank you.
Thank you. And first point out to you that if you happen to look at what the title was going to be, it's not what it was going to be. But beyond that, I'd like to start by thanking Czaslaw and the other organizers for inviting me back to Boltzmann-Gasse so soon. But I have to apologize for changing the title at the last moment. I struggled quite hard to condense my original talk into the allotted time, but in the end, a factor of 4 condensation was just not doable. So instead of that, I want to describe something that's shorter, although it still might be a struggle to fit it in, but something that's shorter and that also fits into the subject of this meeting because it has to do with the interpretation of relativistic causality in the quantum world or in quantum theory. Specifically, I'll introduce a new sort, what seems to be a new sort of causality condition, whose name you see there, persistence of zero. And I'll explain what I mean by that and in what sense it seems to play the role of a causality condition. Unfortunately, to really explain it properly, I would need you to know the framework which I would have presented had I been able to give my longer talk. So despite that, I'll do my best to introduce whatever we need as we go along. Unfortunately, there's no published reference to this fully, but there is something that has some background information about it, which is this paper, A Bell Inequality Analog in Quantum Measure Theory, which you can find, among other places, in my website. So to begin with, let's review or recall what we know about the CH-SH inequalities, which arise in the context of a EPR-like experiment, and very widely studied and well-known inequalities of the Bell or CH-SH inequalities. And it's generally taken, the lesson that's drawn from that is that they show that quantum mechanics is not locally causal, at least in the classical sense. But we could ask, maybe we could claim that if we introduce an appropriate quantal sense of causality, that quantum mechanics is causal, locally causal in that sense. So just to have fixed ideas, a more definite context, consider the 3 regions that are familiar, or at least 2 of them are familiar in the EPR kind of setup, the region A and B. The region Z you can think of as in the past where the sort of EPR entangled pair was created. One particle went off to A, one went off to B. And then in A and B you might have, say, Stern-Gerlach set up. And there are different types of events that are possible there, namely the particle emerges in the upper beam or the lower beam, and so on in region B. And so I'm going to use the little letters A and B, A prime and B prime, to represent those events, or those outcomes, if you like that word. And the prime, I don't know a good notation for this. It always seems to get too difficult to read and confusing, but to try and simplify as much as possible, I've used the small letters without the prime to show one setting and with the prime to show the corresponding outcome with the other setting. Okay. And so here we see the 3 regions, common familiar regions, and I'll be talking about events in the regions. So to think of an event, and I just gave an example of the particle emerging in the lower beam or the upper beam, and so on. The precise definition of an event will be a set of histories where history means a complete description, as complete a description as you can give. So, for example, a set of particle trajectories. So since we, in the simplest case, well, the case that the CH-SH inequalities originally, and as far as I know, still apply to, you have you consider 2 settings in each of A and B. And so by mixing and matching them, you have a total of four different possibilities, 4 different pairs of settings. And for each setting, you have a set of events, which are all what the particle could have done with that setting. Don't worry about this yet. This is just something that I forgot to write on my slide, so I put it on the board. So in that context, let's review the derivation of the CHSH inequality, but in a particular form that was given by Arthur Fine, which will be important for this talk. He broke the basic idea is that some causality condition, this is all classical now, that some causality condition leads ultimately to these inequalities, and then you do the test and you find that the inequalities are violated. So in some sense, causality or local causality is violated if you think classically. But what Fine did was split the derivation, the path that leads from the causality assumption to the inequalities, into 2 pieces. The first piece, by introducing an intermediary, which I'll call patching. The first piece is the deduction that if you assume patching, then you get the inequalities. Now, patching is my short name for the existence of a joint probability distribution for all the settings and all the outcomes taken together, even though experimentally you would never realize that, or actually you can in a certain way, but let me not get into that. But normally they're regarded as counterfactual, but if these probabilities do exist, then you can derive very quickly the CHSH inequalities. The second half of the deduction, which actually logically comes before, is that this causality condition of screening off, which I'll make precise just down here in a second, this causality condition of screening off implies patching. So when you combine those 2 implications, you get a chain of implications. Screening off the causality condition implies patching, and patching implies the inequalities. And what will be important for this talk is the first implication, or the second in the order I gave them, the logically first one, that screening off implies patching. So let's see how that works. The other one is very short also. So the way that the screening off implies patching goes, well, remember what I mean by patching. We had 4 possible sets of settings, A, B, A prime, B, so on. For each setting, you have a certain number, in this case, let's say 4 different probabilities for what can happen in region A and B. And so you have these 4 sets of probability distributions. By patching, I mean that you can amalgamate them all into a single probability distribution, which now depends on A prime, B, and B prime, in such a way that when you marginalize, that is, when you sum out the ones you're not interested in, you get back these 4 probability distributions. Okay, so now the principle, the causality principle that's introduced, sometimes called the Reichenbach's principle of common cause, is that if there are correlations between A and B, it should be because there's something in this past region, either this past region or this past region. I actually forgot to say why I drew 2 of these, because sometimes people consider this one, which is kind of the intersection of the past, the common past. Sometimes they consider this one, which is more like the union of the past, in such a way that regions A and B belong to the domain of dependence of Z. So, or another way of saying it is that within Z, there's something that can serve as a Cauchy surface for the regions A and B. The distinction won't be too important, but it'll play a little role later. So I'm not going to specialize which one we have in mind. The main thing is we just have a past region and 2 future regions. So now the assumption is that that this common cause, little z, will, being an event or a history, ultimately, in region Z, is the common cause. And that's expressed by this so-called factorization condition, which says if it's this equation here, I'm assuming you can see can everyone, yeah, you can see the cursor, right? I hope. Okay, so it's this condition here, which if you divide through by p of z, you can read as saying that the probability of A and B conditioning on Z is the product of the conditional probabilities for A on Z and B on Z. This we assume. This is the input, the causality input. Once you've assumed that, you can make an ansatz, a patching ansatz, as follows. You define, remember this is what patching means. We're trying to define a joint probability distribution for A prime, B and B prime. And we're actually extending it to have also Z. Yeah, Bill?
Sometimes you have P of Z and D, and sometimes P of D and Z. Are they supposed to be the same?
P of Z alone, like here?
No, P of Z, B, P of B, Z.
Oh, that's exactly, yeah. Sorry, yes, they're meant to be the same. I wrote it this way so it would look more symmetrical, but obviously I slipped somewhere. Yeah, so this is the shorthand. The product is the shorthand for and or intersection. So A intersect B and B intersect A are the same things. Okay. Yeah, they're meant to be the same. So once you have made this assumption, then you can make an ansatz, which has now joint probability distribution for A prime, B prime, and Z, just by multiplying together all these pairwise probabilities and dividing through by an appropriate power of P of Z. And having done that, you get this joint probability distribution with a sort of extra variable, but you didn't necessarily want that, so you sum over Z to get just the arguments that you want. And then it becomes like a one-line proof or something. It's very easy to check that if you make this ansatz and then you sum out, for example, A prime and B, you'll get the correct probability distribution for A and B prime, and so on, whenever you sum out the ones you're not interested in. So that's all very nice, and it suggests to us that the indicator that screening off function is a causality condition is that it led to patching. If we take that suggestion, then when we go to the quantum case, we can say that we can take the point of view that whatever will imply patching in that case is the causality criterion that we are seeking. In a slogan, patching is the seal of relativistic causality. So we had these relationships. It turned out fine actually proved the converse, but it's not important. The main relationship is that chain of implications. If we can carry those relations over to the quantum case, then that can justify our saying that quantum mechanics is locally causal after all, but in a quantal sense, not in the classical sense. So can we carry over that those implications? Well, to make it a precise assignment or a precise task, we need to have some framework, and the framework I'm going to use, which makes the analogy with the classical case most clear, is a path integral framework, which goes by the name of quantum measure theory. So I'll have to say a little bit about what is quantum measure theory, and then come back to trying to find whatever causality, whatever condition we can find that will yield patching. So the central quantum measure theory, I abbreviated as QMT, the central mathematical object in quantum measure theory is what's called the decoherence functional. It really should have been named the coherence functional, but for reasons that I don't fully understand, it was named decoherence functional. I think I know the reason, but anyway, it's a misleading name. But really what it is, it's the function of quantum interference between two histories or two events. So classically, given an event, in this case it's the conjunction of the events A and B, A intersect B, as sets of histories. Given a particular event, classically we had a probability for that event. In the quantum case, instead of having a single event, we'll have two events or two histories, and instead of having a positive number probability for them, we'll have a complex amplitude. And in this case, I've introduced a bar notation, not that it means some operation applied to A, but just it's another variable in the region A, and there's no prime, so I can't use prime because that has another meaning. So I've called it bar. So we have, for any two events, we have an amplitude, this decoherence functional, and it's a feature of standard quantum mechanics, and it's made an axiom in quantum measure theory that it should be a positive Hermitian matrix, which is additive in each of its arguments, just as classical probability is additive in its arguments. This setup defines what Jim Hartle calls it generalized quantum mechanics. And from it we get, once we have the decoherence functional, we get the quantum measure by this expression, d of e comma e, which if you unpack what the histories making up the event E are, which I've called x or x bar, and you sum this amplitude for x and x bar over all the histories, you get what's called the quantum measure of E, which would have been, in some sense, the subject of my other talk. This formula comes from a double path integral, often known as a Schwinger-Keldysh type of integral. It reduces to an ordinary probability when E is an instrument event. So in other words, it allows you to reproduce the Born rule. And it satisfies the three-slit sum rule, which expresses the absence of third order or more generally higher order interference. I could say a lot more about it, but I hope that's enough to get us going. So now let's remember where we were. We're trying to find the quantum analog of this chain of implications. I put a C now for classical screening off, implied patching of classical probability distributions, implied the CH-SH inequalities. What we know for sure how to do in quantum mechanics is the second half. Patching can be given an obvious definition, just writing down, instead of a joint probability distribution, you just need to find the joint decoherence functional, which when you sum out the unwanted settings, you get back to the decoherence functional that's directly measurable from the settings. So that's patching. And you can go through the chain of deductions that led to the CH-SH inequalities, and you get something else called the Tsearelson inequalities, which are a known set of inequalities that quantum correlations need to satisfy, just like classical ones would satisfy the CH-SH inequality. So one sees in this a precise sense in which the Tsearelson inequalities are the quantum counterpart of the CH-SH inequalities. But what about this question mark? What causality condition do we put in place of screening off that will give us patching? Just as there was an obvious analog of the patching condition for the decoherence functional, you just basically write every letter twice, once with a bar on it and once without. Just looks a little harder, but it's essentially the same formula. Just as that exists, there's also an equally obvious quantum analog of the classical screening off assumption, this factorization. Unfortunately, when you try to plug it into Fein's ansatz, it fails for different reasons, but the most obvious one is you end up dividing by 0 sometime, because although it's not harmful to divide by something whose measure is 0 classically, what can happen is, quantum mechanically, you can have two events whose measure is not 0, but their inner product, the decoherence functional between them is, and you end up dividing by 0. So as far as we can tell, we cannot use Fein's ansatz. And therefore, this quantum screening off cannot be the causality condition we're looking for. So instead, the suggestion is that there's something else, which is in the title of the talk, that I've called persistence of zero, and that's going to be our missing causality condition. Unfortunately, again, to explain what it means, I have to introduce one more bit of mathematical structure, which is Hilbert spaces and Hilbert space vectors associated to events. So with the aid of the decoherence functional, because it was a positive Hermitian matrix, we can use what's called the Gns construction, for those who are familiar with the terminology, and produce a Hilbert space from it. Basically, we think of the entries in the decoherence functional as inner products of corresponding vectors, and that defines for us the vectors themselves up to unitary equivalence. And so once we have for each event in a region, we have a vector, then we get all the vectors and their linear combinations, we get a Hilbert space for every region. So for example, here the Hilbert space for the region AZ. I forgot to write it down, so I put it here. You can think of this as the rule that takes you from the decoherence functional to the vectors. You seek for every event a corresponding vector such that this equation holds. And it's unique. I mean, now, using that, I can say what persistence of zero means. To describe it, I only need two regions. I don't need Z, A, and B. I just need an earlier region and a later region. So let's, for example, forget about B for now and just take Z and A. Okay. Now, what does persistence of zero say? Well, suppose Z are a bunch of events or histories, but let's say a bunch of events in region Z, little z, such that their linear combination with appropriate coefficients, psi of z, vanishes. I mean, there'll be many such linear relationships because the decoherence functional generally is highly degenerate matrix. It has many zero modes or zero eigenvectors. There'll be many such relationships. So take one of them, any one of them, and now go up to region A and say, for each event, we're interested in the event that little z happened, and then some event, little a, in region A happened. That gives us a mapping from events in Z to a map to events in Z union A, and then therefore in the corresponding vectors from little z to A and Z. And what persistence of zero says is if there was a linear dependence here like this, exactly the same linear dependence with the same coefficients is still true when you go up to the later time. So you can see why it's natural to call this persistence of zero. The zero here persists when you perform the operation of and then little a. Now this persistence of zero holds in unitary quantum field theory, and in fact it follows from the double path integral. So the final thing I need to do is now show you why the persistence of zero does lead to patching, although we'll see that we'll need another auxiliary condition to finish the proof. The proof comes, I won't give the proof, it's a little too long. It comes from the fact that the persistence of zero lets us build what are called class operators for the events in regions A and B. These so-called class operators are operators, I put hats on them to show operators. They're operators, one for each event, which have the relations which are typified, relations related to the decoherence function in a way that's typified by this equation. So I'll just let you read it. The main thing is that this decoherence functional becomes a matrix element of products of these operators. If we make a further assumption, which is that the Hilbert space in region Z is actually the whole Hilbert space, then it turns out that these class operators, which a priori went from one Hilbert space to another, can all be regarded as mapping the same Hilbert space into itself. Once you have that, then you can form products of the operators, and that lets you make this ansatz for what I'll call quantum patching. And again, it's even longer, and I won't attempt to read it, but I'll let you read it. But you can say it. You can see it has a very similar form to above, just with more operators for all the different possibilities. For those who are familiar with the so-called ABL formula, you'll recognize the strong affinity in it. And then, again, it's a very short calculation. Once you have this, to show that the marginals come out correctly. I should say that this extra condition we had to supplement in the proof, supplement persistence of zero with, this holds in quantum field theory on the right-hand side. If the region Z contains a Cauchy surface for A and B, then this equality of the Hilbert spaces holds. So that's the main thing I wanted to present, but let me finish with a few somewhat more general remarks. So just to review, we've proved, or I've just claimed and shown in part, that we can prove that patching does follow from this new causality condition of persistence of zero. However, the proof only works, as I gave it, when this extra supplementary condition holds, that equality of the Hilbert space of the past with the full Hilbert space. In some sense, it's true in most cases, but I think it's not likely to hold in cosmology because, among other things, for what are called, and therefore in quantum gravity not likely, because of what are called trans-Planckian issues. So we have to ask then, what could replace this condition? And the conjecture is, well, let's go back to quantum screening off, which didn't in itself do the job, but the conjecture is that it can replace this other condition so that persistence of zero plus quantum screening off does imply patching. So that it's not a settled conjecture, but I think it maybe could be settled. And having said that, let me make a couple of very general comments, even more general comments. One of the motivations for this work, if not the main one, was the hope to define relativistic causality in a way that it would carry over to causal sets so that we could use it to produce a quantum dynamics for causal sets. However, there's two things standing in the way. One is I'll call a hurdle, and the other one, in other words, it must be overcome, and the other one is a philosophical doubt. The hurdle is something that everyone who works on quantum gravity really faces at one time or another if they get far enough, which is that to talk about things like persistence of zero, I had to say which was earlier and which was later. Events in A were later than events in Z. But when you have quantum gravity, of course, the causal structure itself becomes, in some sense, indefinite. So the kind of thing that Čáslav has been spending a lot of effort on. The more general philosophical doubt is, I won't even try to explain where it comes from unless you ask me, but harking back to Stefano's talk, for example, and in causal sets, non-locality is an essential feature. There's more and more evidence that quantum gravity will be non-local. My own feeling, I've been unable to convince myself anything other than once you accept non-locality, even classical screening off is really not a well-founded assumption. But if not that, then what? And this leads us off in a direction that, as far as I know, has not been explored at all. And so that makes, I think, a good place to stop.
Thanks for the talk. A lot of questions, but I just wanted to come back to the statement that local causality is violated by quantum mechanics, right? Where local causality is defined in a classical sense.
Yes.
So in Bell's papers, he never talks about the classical sense of local causality, right? He just talks about local causality, full stop. And he defines it in terms of local beables and then calls it a relativistic spacetime, right? And probabilities attached to values of local beables in the space-like separated regions of this relativistic spacetime. Which aspect of Bell's definition of local causality that you call classical sense is given up or
right, so good question.
in the quantum sense that you call?
Yeah, two things, I would say. One is attributing probabilities to events, and that the probability sum rules are obeyed. But as is well known, quantum mechanically, probabilities, or the quantum measure, which generalizes the probabilities, doesn't obey those because of interference, right? So that's given up. In fact, this three-slit sum rule, which is obeyed by quantum mechanics, shows precisely the sense, the degree to which you've given that up and the degree to which you have not given up. The second thing, which is more radical, I think, is that when you go far enough, I mean, I haven't directly addressed issues of quantum foundations here, but they always are lurking somewhere relatively shallow beneath the surface. The second thing is the assumption, once you have a notion of what kind of histories you're dealing with, what's this kind of physical system, that reality should be described by a single history. That's what it is classically. I think that also is going to be given up, although it didn't feature in this discussion, but I think to come up with a correct conception of what microscopic reality is like, you need something related to histories, but not quite individual histories. But as far as what we saw today, it's the assumption that you can apply probabilities to events, because of course the CH-SH inequalities are all about probabilities and the Kolmogorov rules for probabilities.
Can we, sorry to interrupt. Don't forget we have a discussion section at the end of this session. Thank you very much. Okay, thanks. Let's thank Rafael once again.